welcome to the flap of a butterfly's wing. It's our chaotic, unpredictable weather event, and you've got just the right background, Rick. I see that, of course, I'm just sitting where I always sit, but thank you for being here. My name is Ann Merchant, and I am with the National Academy of Sciences, and we are back. And of course, I couldn't be back without you. As always, I am joined by
I'm Rick Levert. I'm the program director of the Science and Entertainment Exchange, a program of the National Academy of Sciences.
That's right. And we've taken a little bit of a break, but we presume that you don't need us to explain very much about what the National Academy of Sciences is or does. Although I always will hand it over at some point for Rick to give a little bit of explanation about the exchange. But I will ask Sachi to drop a couple of links into the chat because we do have some resources from the Academy that are relevant to today's event. One is something from a program that is called From Research to Reward, that is meant to showcase the way in which some of the research that is being done is relevant in some surprising ways. And one of them is on, it was the way in which physics, data, and computer sciences have been really beneficial to weather prediction. And she's already dropped that into the chat. And the other is an initiative that we have at the Academy called Based on Science, where we quickly answer some very specific questions with some easy to follow, very simple, straightforward facts from science. And thank you, Sachi, for dropping that into the chat. And this one is, again, on the butterfly effect and the complications that chaos theory poses when we're looking at predicting weather. But of course, a lot of the work that the Academy does comes in the form of big, giant, complicated policy reports. And we know that's not for everyone. We hope that there are people in our audience that do like to read those, but it's not for everyone. And so that's one of the reasons that the Science and Entertainment Exchange was created. And this, of course, is the perfect segue over to you, Rick.
Great. So if you are a writer, producer, director, studio executive, actor, storyteller of any kind, novelist, you have a question about science, you can call us, and Sachi's going to drop the number down there. There it is right there. And we will find someone who can answer your question and connect you to them. It's pretty much as simple as that. We've done it over 3,400 times, including so many of your favorite TV shows and video games where grown-ups are running around with capes on and masks. That's kind of our jam. By the way, I'm going to recommend something that just came out that we did do some consult work on, which is Paper Girls. That's Stephanie Folsom created it for TV. It's on Amazon Prime. Anyway, I have no affiliation with it other than that we did the consult, but we have been enjoying the show. So good on you, Stephanie. So if you are a STEM professional and this is your first time hearing about the work that we do and you'd like to become a part of it, please drop us an email, drop us a line, give us a call, whatever it may be. We're always looking for new people in new areas, and storytellers are always coming to us with questions for which we don't have experts. So we would love to hear from you. So today we're going to be recording the show as usual. It's going to land on our website later this week, probably on Friday. You can subscribe to the Science and Entertainment Exchange on YouTube to see these events and other videos like it. Also, our Ask a Scientist series, which is about to get a big facelift. So we're really excited about that. Hopefully you'll be seeing that in the fall. And you can also sign up for our Collider newsletter there. So everybody who RSVP'd to this will get a link to the video of this after the fact. So you can see it there. I'd like to thank our sponsors today, Howard Hughes Medical Institute, without whose support we would not be able to do any events whatsoever. So thank you very much. And also we get major funding from the Alfred P. Sloan Foundation. And I also want to thank individual donors like many of you who gave today. Thank you. That goes right back into this programming. And we're actually going to start some in-person programming as well. So if you are in LA or New York especially, but sometimes other places on limited engagements, we will be doing live programming again this fall. So we're very excited about that too. Today, in a moment, you're going to hear from an amazing expert, my favorite meteorologist, Tom Di Liberto, and Ann will tell you more about him in a moment. But when he starts speaking, actually, even right now, if you have a question about meteorology or climate, really, you can just drop it right down here into the Q&A. And I'm going to come back on after Tom is done, and I'm going to get to as many of your questions as humanly possible. And then some of you also signed up for our VIP Q&A, which will be happening on video chat after. You should have a separate link for that. If you don't, please touch base with Sachi, and I'm sure she can help you out. But this would be for people who are either exchange supporter level people or people who signed up for it specifically today. So if you have that, we'll see you there. My rabbit hole this week is an article I found that's just got a really nice overview of meteorology. Usually I go for more wacky stuff, but let me just tell you, if you type in your little Google bar, meteorology fail, that is hours of entertainment. So please, I encourage you to do that as well. Anne, back to you.
Well, I went a little more highbrow with my rabbit hole. I ended up looking at butterflies. And so I found something called A Brief Fluttering History of Butterflies in Art. And of course, you would imagine that much of the symbolism is on metamorphosis and change, but there is a really interesting visual history of the ways in which butterflies have been used in art. So thank you, Sachi, for putting that in the chat. So we've gone from, your fails to my lovely depictions of butterflies in art. So we are very happy when we started to think about how we wanted to come back, and we did take a bit of a break for a variety of reasons, and we're glad that you've come back with us. We thought, well, August, what's happening in August? What might be appropriate? Well, August is hurricane season. And as Rick said, Tom is our favorite meteorologist. And I have to say that when I first met Tom, this was at a meeting where they were featuring what they were calling America's Science Idol competition. And it was a fairly big competition with a lot of people that had entered this, and there were multiple rounds, just like with American Idol, the singing competition. And I saw Tom give his presentation at that event and had to go through a few rounds, and he won America's Science Idol. And because I am always talent scouting, I ran up, got his information, and like many people that become involved with the National Academy of Sciences, he has never escaped our clutches since. So when we thought about doing an event, we said, well, there is only one person who can do this. And thank you, Tom, for agreeing to be here, because when else would we have America's Science Idol on our stage? And so thank you. Thank you for being here. And thank you for agreeing to talk about the butterfly effect, because we think it's pretty cool. So we're turning it over to you and letting you take it from here.
And the funny thing, I don't think they ran that competition again. So I'm still the reigning America's Scientist Idol. So, hey, my mom was very, very proud when I won that award. So, hi, everybody. I'm Tom Di Liberto. I am a meteorologist and climate scientist by training. I work at the National Oceanic and Atmospheric Administration, or NOAA. Specifically, I'm the climate scientist at climate.gov. If you've ever interacted with the NOAA climate handles on either Instagram, Twitter, or Facebook, that's also me. I'm the social media lead for all of the NOAA climate stuff. And I do a lot of science communication work, but I also do a lot of broader stuff when it comes to climate. I was at COP26 last year with the United States at the U.S. Center for the big climate conference that goes, and I'll be going back later this year. But today I'm going to talk about something near and dear to my heart: butterflies and chaos theory and the weather and the atmosphere and all that good stuff. Hopefully I won't ramble too much, but you never know. But I'll talk for a little bit. Can everybody see that slide? Is it working for everybody? Thumbs up.
Looks good, man.
Cool. So obviously this is an image to scale of a butterfly in a tornado, but let's talk about this idea. Butterfly wings. You may have heard of this saying before: a butterfly flaps its wings somewhere and it leads to a thunderstorm or a tornado somewhere else. It's beautiful. It's very poetic. I feel like it has a lot of deeper meaning in people's life. It's also sort of not true on the way you're thinking about it. You do not have to be worrying about the life cycles and the activities of butterflies in South America if you live in the United States, being like, oh no, is it gonna rain on my party this weekend? You don't have to be looking to see what monarch butterflies are doing somewhere else. But it's not true, and I'll get into that a little bit. Basically, the reason why I say it's not true is It's similar. If you imagine the guy, you've seen these commercials before where someone's jumping up and down on a Tempur-Pedic showing how amazing it is. And you can't even like knock over this glass of wine over there. That's pretty much what's happening in this situation. A butterfly flapping its wings is only kind of disrupting the atmosphere around it over a course of several inches. And then the atmosphere kind of damps it out. That sort of influence is kind of small out. So it'd be like this, and you don't have to worry about, that sort of thing. But there is another reason why that saying holds true in weather. It's not necessarily the butterfly's wings itself, let's say, is causing the thunderstorm and tornadoes. It really is a story about how we can forecast the weather and how we can tell the future. So the bigger part about this is we have to recognize the atmosphere is interconnected. Any weather that you're seeing outside today is coming from somewhere else in another day, year, week, month. It's all kind of interacted. So this idea that what happens in the Indian Ocean can easily affect the weather and climate here in the United States, or it can affect the weather and climate in South America or in Europe. This is not out of the ordinary. This is not crazy to think about. This happens every single day. A major storm that comes across the United States started 4 or 5 days earlier coming off of Asia. Right? So this idea that this atmosphere is all interconnected together. If I put this image back in time, you'd be able to see that, even though you may not know exactly what days. I personally don't even know what day this image was taken. I just took a random date. I took one of those websites and I spun the time. I just chose a random date because that's pretty much true. The weather always comes from something else. But remember, I mentioned that's this idea of chaos theory and butterflies. What does it actually mean? This idea of a butterfly flapping its wing causing a thunderstorm, and how it's more related to the way we talk about how we model the atmosphere, how we forecast the atmosphere. Well, first things first, we can't monitor all of Earth. These are pretty much what I would say are your best locations for surface observations on our planet. About 9,000. For one, you'll notice the oceans are pretty empty. Antarctica is pretty empty. There's huge parts of the Sahara that are empty. South America too, the northern Arctic, getting places in Central Asia. This is it in terms of surface observation. And yes, satellites can help us get a better idea of what our atmosphere looks like, but we will never have a complete view of what's going on in our atmosphere. So that means, how do we forecast it then? We know from the get-go then that when we're trying to predict what our weather is going to be in these weather models, you're basically just think of them as like computer game versions of Earth that we created with codes. We know from the get-go we don't have every bit of information in them, which means right from the beginning they're wrong, because we know we can't have all of that information. Because what I say about chaos theory and this butterfly flapping in winds, it's really the story of uncertainty and how we don't know what's going on. This is an image. Each of these Earths is a different weather model run of prediction about what the Earth may look like. Each of these could possibly be right. And each of these, by its very nature, is wrong. And why is it wrong? Because of chaos theory. Because of the fact that little errors in the beginning, missing, let's say, a butterfly's wings, to that poetic way of saying it, that tiny error can grow to a monster in our weather models in several days. There's a certain amount of time. And that is a story of chaos theory and how we forecast things. Here's a good example of this. On the left there, this is 21 different weather models. Each of those lines, just think of it like, don't worry about what it's actually predicting. Just note that they're all pretty much on top of each other. So each of these different weather models that we can be using to forecast the weather are slightly different. They're not majorly different. They're slightly different. Itty bitty differences between the two of them. You can see like the lines are pretty much on top of each other, but they're not exact same. At the very beginning of this weather model run, pretty much the same. Now look on the right. That's 15 days later. Those itty bitty errors, itty bitty differences between the models basically leads to chaos, madness after 15 days. There's no consistency there in what any of those weather models are predicting at 15 days out. They're all over the place. And the reason for that is that even though these similar models look very, very the same in this image on the left, those tiny differences grow and they grow and they grow and they grow, getting so big to dwarf out any of ability of these weather models to predict anything in our atmosphere because of chaos theory. So with this idea of butterflies flapping their wings and leading to tornadoes, it's not really that. It's more about this sort of way of predicting it. Now, you might be thinking, okay, Tom, you've just convinced me to never listen to a meteorologist again. Cool, I'm out of a job. No, don't listen to us because we can still tell information. There's a point at which I would say don't even bother looking at a weather forecast. That point, I would say, is roughly 10 days currently. Any weather forecast is giving you a specific, like, high temperature and low temperature after that. Nonsense. But the key thing to note here is, one, this is looking at how weather models, a specific weather model, has improved since the 1980s to today. And basically, higher up on the y-axis is good, lower is bad. Blue is a 3-day forecast. The red is a 5-day. The green is a 7-day. And the orange yellow is a 10-day forecast. And you can see that, one, our models have gotten better. Two, a 3-day forecast is pretty darn good nowadays. And then three, a 5-day forecast made today is probably as good as a forecast made in the 90s for a 3-day forecast. And even then, a 10-day forecast is going to be accurate or pretty good most of the time. But basically that's pretty much the limits, I would say. It's probably around 14 days. But with our current weather models, I would say 10 days is the limit to how well it's good. Because again, this is a story about, chaos and how things grow. Now, you might also be thinking, Tom, you're a climate scientist. You talk about climate. Are you saying that climate models can never go out past 10 days? How can you forecast or outlook climate beyond 10 days? What's this conspiracy going on? Well, climate models are not weather models. They're forecasting different things. Now, what does that mean again? How does that make any sense, right? Weather and climate, they seem similar to each other. Well, here's the fundamental difference between weather and climate. All of these individual white things you're seeing is creating weather where that person is located underneath it, right? Now, if I asked you, let's say, to pick some clouds over the United States, let's say these clouds here over the United States, and I say, where do you think they're going to? If I animated this, where do you think they'd move to? Now, probably none of you have ever seen this image before. Maybe most of you aren't trained meteorologists or have even predicted the weather again, yet you might have an idea about where those clouds would move to. Why? Are you magicians? Are you witches? Why would you know that? It's because you know the climate, right? So these individual events, you may not be able to predict when they're going to happen, but in general, the flow of how things normally act, the climate, you guys kind of know because it's based on your weather experience. I always say climate is basically weather memories. It's what you expect things to happen normally. And that's the difference between a weather forecast and a climate forecast. A weather forecast is a very specific thing. I am forecasting it to be 85 degrees with a low of 62. A climate forecast is now you got to change your frame of mind to think about how different than normal it's going to be. I think the temperature is going to be above average. It's going to be you do something different than average. And that slight difference changes the way or the ability for us to forecast. We do a much better job. We can forecast much longer periods of time if we're saying things based upon the difference from average than we are than saying it's going to be a specific temperature and a specific amount of precipitation. So again, climate models are predicting the abnormal. In percentages, we're never going to say 100%, we're going to say it's about a 70% chance it's going to be above average, a 30% chance it's going to be below average. But a weather model and a weather forecast, you're predicting specific things in like absolute numbers. If I say, tomorrow the temperature is going to be above average to you, and you're like, that doesn't mean I understand necessarily what I'm supposed to do tomorrow. You need like a specific number. But if I'm going to tell you the season, let's say, it might be above average, below average temperatures this winter. You might be thinking, maybe I should be prepared for colder temperatures if it's wintertime and where I live. That's the difference between the two of them. Give me another example is a hurricane. So weather forecasts are predicting the exact location of the hurricane. Each of these lines, by the way, is a different weather model, showing again the uncertainty, the chaos. Slightly different models create a wide range of potential answers. Chaos blowing up, errors in this. Weather forecasts are predicting the exact location and the strength of it, the timing. Climate forecasts are the seasonal predictions. So this is the most recent. This literally came out earlier this month, looking at the seasonal predictions for hurricanes. They're not predicting exactly when a named storm is going to make landfall or how strong that individual storm is going to be. They're giving you broad numbers. There's going to be about 14 to 20 named storms, 6 of 10 of which are going to be hurricanes, 3 to 5 are going to be major hurricanes. And of that, I'm still giving it about a 60% chance of it being above average. And that's the difference between the two ideas of that. But you can see there's lots of uncertainty associated with this. Basically, chaos is still working on climate timescales, just in a different way. And that's why when we talk about climate forecasts, it's all about playing the long game if you're a betting person. Meaning that, yeah, if someone says 70% chance for rain, or 70% chance of it being above average over a season, there's still 30% chance it won't be. But over the long run, those things will be able to help out. This idea of climate change, then, well, we can learn from our past and on physics to be able to force our models. And the difference here when we talk about chaos theory, adding in error into our models, is that signal can rise from the noise. So you can see here, the current warming is unprecedented in the last 2,000 years. And if you look at our models, you can basically see that the noise of the human influence easily pops out of the signal of the human influence easily pops out. And then this area down here, the simulated natural, that's almost the noise of what would be natural chaotic atmosphere, almost of what could naturally happen. This is that range of what's happening. And we're clearly seeing a signal jump out of that noise, which is also why we can take these looks at projections for the future and have more confidence in them, because a weather image will be like a lot of up and down. We're not going to be able to predict that random up and down of, because of chaos, because a season can be weird. Mother Nature can do random things on a year-to-year basis. But the smooth line is the climate. And that's kind of the signal that can rise above that chaotic noise of the weather. So I want to stop there. There's lots of talk about when it comes to weather and climate, and I'm more than happy to talk about literally anything you all want to talk about as it relates to our atmosphere. I say I love our atmosphere because everything is interconnected, and it is something that I can talk to anybody on any continent on this earth about the weather and not know their language and still have a connection with somebody and talk about the weather, because almost everyone has a story about them interacting with a bad thunderstorm or getting snowed on or being too hot or too cold. And I love the fact that atmosphere does not know borders. It just does what it wants to do. So I'll stop there, and I'm looking forward to the conversation.
Okay, so great talk. I'm going to lead off with a question from Jorge. How important are El Nino and La Nina in causing hot summers and cold winters?
Oh, now you're talking my jam. I'm actually also one of the El Nino and La Nina experts at NOAA. So I'm one of the forecasters of it. Our forecast comes out on Thursday for the August update. El Nino and La Nina can play a huge role. So for folks who don't know, El Nino and La Nina refers to either a warming of El Nino or a cooling of La Nina of the central and eastern equatorial Pacific Ocean. And what that does is it basically takes the atmospheric setup over the tropics and just jumbles it all up. And that pushes over an atmospheric domino, and it leads to changes of the jet stream where we live in the mid-latitudes, which can cause all sorts of havoc, mainly in the wintertime. So globally speaking, El Ninos tend to lead to there being warmer than average years, and La Ninas tend to lead to there being cooler than average years. But it literally can affect only like 30 to 40% of Earth's population can be impacted by a La Nina or an El Nino in the Pacific Ocean. Although, interestingly enough, it's not like El Nino or La Nina is increasing the amount of crazy things that happen on planet Earth when it relates to climate. It's not like it's creating a given year, whether it's El Nino or La Nina or not. Those will pretty much have around the same number of like weather extremes. But during El Nino and La Nina years, the difference is we know where they may happen ahead of time. So you tend to be able to prepare for them in those individual areas. But in a given year, they could happen literally anywhere.
So Karen actually wanted to she asked you to elaborate a bit about the jet stream and how it interacts with climate change.
Sure. So the jet stream is a fast area moving winds about 30 to 40,000 feet in the atmosphere. It serves as kind of like a storm highway. For one, basically storms hitch a ride and they get traveled west-east where we live in the United States. It can get wavy at times. It also kind of serves as this boundary between colder air to the north and warmer air to the south. So when it gets all jumbly, that usually means that cold air is going where cold air normally doesn't go, and warm air is going where warm air doesn't normally go. Another thing to think about, it's almost like if you think of it like in terms of a stream, if you think of the Mississippi River or the Amazon, when it's roaring at its fastest, that is not a meandering river, right? That is a straight river. And so when the jet stream is strong, it is blowing really strong west to east in the northern hemisphere. If it's weaker, it's like more like a meandering river. So if it's weaker wind speeds, then it starts to meander. And those meanders are where things get crazy. So a meander basically leads to almost like a blocked pattern. It's almost like there's someone threw a giant rock in a little like a creek or something like that, and now it's slowing down things and the water starts meandering a bit. And what basically happens if you block that flow and you set in these meanders, that's when weather extremes happen. So if you think to bad heat waves, if you think to really cold air outbreaks or warm air outbreaks in the wintertime, it's usually associated with those sorts of atmospheric patterns where the jet stream gets super duper wavy and just kind of gets locked into place for a while, where someone's stuck under a big loop up or a big loop down. Now, climate change, there is some research out there suggests that because the Arctic is warming so much faster than anywhere else on the planet, 3 times as fast, or even more so, depending on the time period you're looking at, it's causing the jet stream to get weaker and meander more, leading to these more outbreaks, so these cold air outbreaks and whatnot. Now, if people ask me all the time, well, if climate change is so settled, what's still confusing for folks? Where is the argument still ongoing? This is a really active area of research. There's other research which suggests that's not happening. You can't blame that on the Arctic, at least in the wintertime for that. It has really big repercussions because we know the jet stream and its influences can have a huge impact on weather across the planet. But it's certainly an area that's a lot of smarter people than me are actively researching, and I'm sure another dozen papers will come out on it in like the next 6 months or so that I will be reading, and I'm looking forward to seeing what they say.
So Edward and David have a similar question about effectively controlling the weather. And Edward specifically wanted to know about, are there places where you might be able to go that would would allow you to have more control over the weather? And David is more asking about, is it possible to control the weather more in the future?
Right. So this is an interesting, cloud seeding, I feel like it's been going on for decades now. The problem with it is that it's almost impossible to tell if those cloud seeding things actually work. It's hard to see whether the atmosphere is going to do it anyway to be able to tell. But a lot of people have done that. So there've been major, if you remember the Summer Olympics in Beijing, they seeded those clouds ahead of time, hoping to kind of clean out the air, and actually did rain there, but you couldn't tell if that was due to the cloud seeding or just due to the randomness of the atmosphere. It is much too difficult to be able to understand how well we could control the atmosphere or whether we can even do it. The scary thing sometimes when looking at climate and weather especially is that there may be just a fundamental limit to how well we can forecast it. We could have the fastest models in the entire world, the fastest computers, as much information as we want, but because we know there's never going to be a perfect model, there might be a limit of 15 days or so of our ability to forecast. Now, controlling the weather, there are other aspects that you could potentially do. So when you shoot silver iodide, there could certainly be advances in the ability for us to be able to figure out how to control the weather or how to at least affect it in certain ways. When it comes to climate and climate change, geoengineering is an example of this. There are thoughts of, now there's more and more research going into what happens if you shoot sulfate aerosols into the stratosphere, it reflects the sun's light and can cool the atmosphere, and that can lead to weather changes as well. What if you seed iron into the ocean? That can lead to blooms of algal blooms pretty much, and that can change weather. But the atmosphere is so complex. The fear is that we do this one thing, but we don't. It's kind of your classic unknown, there's known unknowns and then there's unknown unknowns, and there's a lot of those when it comes to being able to control the weather, and especially these geoengineering things. We know we don't know everything that's going to happen, and it's always going to be a curveball thrown at you to figure out how things would happen. Yeah.
So David and Mordecai ask questions I think are kind of two sides of the same coin. David wants to know about how much better you do think. I know you just said there could be a limit, but how much better do you think these forecasts could potentially get in what we'll call it the near future?
Sure.
And then Mordecai's looking back and wants to know why the predictions got better.
Both good questions. So I would say for weather prediction, 2 weeks, I think is going to be where we max out roughly, I would say. I think there's some research that came out in the last couple of years that looked at chaos theory and looked at just the way where our ability to forecast with the models that we have, and that around 2 weeks is probably your top line limit. When it comes to climate forecasts, though, we might be able to get more and more skill out of that longer period of time. For instance, an El Nino and a La Nina, we can predict accurately 6 to 9 months in advance, which has a lot of influence, a lot of importance. If you can tell an island nation in the Pacific that, guess what, it's going to be drought next year because El Nino is going to be roaring, they can plan ahead of time for it. And there's still a lot of skill left in that. I feel like there's kind of, we're still trying to figure out that. There are basically, what I'm trying to say, there are certain atmospheric phenomena that we know have big influences on our climate that we cannot forecast more than a couple of weeks in advance. Things called the Arctic Oscillation. If you've heard of the polar vortex before, it's that just made nicer. It's like when you rename a fish because you want people to eat it. Similar sorts of thing. Arctic Oscillation is kind of boring, so this kind of got like renamed the polar vortex. But whether those things happen is really difficult to say because our models do a really poor job in that. So there's a lot of opportunity there, I feel, for being able to forecast those things, which have really big impacts on our ability to forecast it. Why have models gotten better? Why have our forecasts gotten better? The amount of tools available now for scientists to use to forecast the weather are more than at any time in history. We have a better understanding of the uncertainty because we have more models, weather models that we can run. The idea of basically saying chaos, it might seem overwhelming that all of these models are wrong, but if you run a whole bunch of weather models and they're slightly different and they say something specific and they're all very similar, what they think is going to happen, you can have a lot of confidence, a lot more confidence in that weather forecast because all of these models are pretty much put out the same thing, even though we know that they should be diverting, they should be going different places, but they're all kind of one area. It gives a weather forecaster a lot more confidence. And that we could not do in the past just due to computer capability. Our ability to run more models, more folks running models, and of course, better satellite data. You may think, oh, how much the observations that go into a weather model are actually predominantly based off of satellite data, as then you have observations from the surface as well as weather balloons that get launched. And sometimes you have, when planes take off, they can record data on the plane too that gets into our weather models. But the ability to get more of that data into faster weather models. Ooh, I had thunder outside my door. I'm excited. And that has led to that drastic improvement. The difference between a weather forecast made in the 1970s and today is like going to the moon in some senses. A 2-day forecast made in the 1970s, I think, would probably be almost as bad or worse than one made in a 7-day forecast made today. It's just remarkable how well forecasts have gotten.
I think that kind of transitions nicely to Jackie's question. Jackie wants to know, we didn't understand that all the weather on Earth is interconnected until we saw Earth from space. And how rapidly did forecasting change at that point? So do you see a direct line between landing on the moon, going to space, and better predictions?
Most certainly. I mean, I can't imagine trying to forecast the weather prior to satellites. And a lot of things we didn't even know existed. The jet stream was theorized prior to World War II and was only observed for the first time because pilots flew into it and they recognized that they couldn't, they're going right into it and they couldn't fly into it. So that was something that was theorized, and there were no observations until the 1940s. And then yes, when the first the weather satellite that went into space was in the 1970s. It was called TIROS-1. And before then, you're right, it's this idea of things being interconnected may have been, thought about, but like there's no way of doing it until we were able to go into space and see our planet. El Nino is a really good example of this too. It's called the El Nino Southern Oscillation. It's called El Nino because Peruvian fishermen noticed this thing happened about 2 to 7 years, and they called it, most effectively happening around Christmas, they called it El Nino, referring to Christmas and Jesus. The Southern Oscillation part comes from British meteorologists in India. And they noticed that there's this oscillation in the atmosphere in the Western Pacific Ocean. So for a long time, you had El Nino on one side of the Pacific and the Southern Oscillation on the complete other side of the Pacific. And it took until the 1950s for a scientist to say, I think they're talking about the same darn thing. and it became ENSO, or El Nino, the Southern Oscillation. So, like, yes, there's been so many things in our recollection, and this doesn't hold true for weather even. For tsunamis, it's very similar. This idea of interconnectedness, when people, the fact that we can see how these things work on a global basis has led to people going, poof. You can look back in time and just notice that people talk about the same thing. They just didn't realize at the time that they were talking about the same thing because they didn't have the technology that we did to be able to see those interconnections on our planet.
So Lisa would like to know if you can explain atmospheric rivers, in particular
sure.
the one that was in BC, Canada last year.
Sure. So atmospheric rivers are narrow areas of kind of moist air that gets fire hosed at the West Coast, somewhere along the West Coast. Oftentimes in California, for instance, they give about 50 to 60% of the yearly rainfall comes from atmospheric river events. Tends to happen during their wet season, but it doesn't have to be in California. That fire hose can be, I have 2 toddlers, so it's like my 2 toddlers holding a fire hose. I don't know where it's going. I might get wet. The neighbor might get wet. Someone's going to get wet, though, right? So it's somewhere along the West Coast that's going to get hit. And basically what happens, it gets tied to the tropics. The atmospheric pattern of like a high pressure system and a low pressure system can basically lead to a funneling of winds from the south right into the West Coast. And that moist air runs up into the mountains along the West Coast. And as the air rises, it's like wringing out a sponge. And that moist air sponge gets wrung out, leading to heavy rainfall. Climate change is potentially making those air masses more moister. So if you're still pointing them at the mountains, and you know mountains cause rain, but now you've made that air have more water in it because also a warmer atmosphere can hold more moisture, it could lead to there being more rainfall. So that leads into some research, especially on the West Coast, that you might see more weather whiplashes, where like it doesn't rain for a while. You have droughts, which we certainly know is happening across a large part of the West. But then sometimes in the rainy season, it pours, like it pours. And it leads to these other issues when it comes to like an area that first, like for instance, areas that burned lead to the ground becoming less likely to absorb moisture. So that if you get really heavy rainfall, it basically rushes off more, leading to more flash flooding, leading to more mudslides, which is a major concern no matter where you are along the West Coast.
So Harvey wants to know how much impact the Inflation Reduction Act, assuming that it becomes law, will have on global warming and the goal of reducing carbon emissions by 40% by 2030.
So I mean, I only know as much as what I've seen written about it. I think it's in terms of the reduction needed. I think they said it's like 30 to 40% reduction and needed. So I don't think it gets all the way to the goals that we set for 2030, but it gets us farther than we'll get us farther than status quo, certainly. And it's the largest bill to have ever passed focused on reducing. There are some good things in the bill in terms of funding a lot more renewable energy, as well as I believe there's money to fund NOAA, as well as a whole bunch of other folks within the U.S. government for a variety of means for predicting and helping out with disaster research. So, will it solve climate change? No. Was it still the largest? If it does pass, will it still be the largest climate bill passed? Yes, I think is the best way of putting it.
So I think Alan's question is pretty relevant to what you just said then. Wants to know, have we already reached the point that it may be too late to reduce temperature increases and droughts? And if not, when will we have reached that point?
Sure. We will never reach a point of no return. We will never. So I say that in a sense that the best time to act, for climate change, the best time to act was 30 years ago. The second best time to act will forever and always be today, and then today, and then today, no matter what day that is. It's always going to be the present day. And are there tipping points? Yes. Are we close to a tipping point? I don't believe so. I don't believe the science says so. There is still plenty of time for us to take action to reduce our emissions of greenhouse gases, to reduce our warming. Will it be easy? No. Will we be able to avoid some bad things happening? Probably not. I think we're on a pace to at least warm. It's gonna be really hard to keep us at 1.5 degrees Celsius of warming compared to pre-industrial times. But the answer will always be to reduce emissions of greenhouse gases to zero as fast as possible. There's a big difference between running into a wall at 15 miles an hour versus 75 miles an hour. And that's what we're trying to do. Just always just kind of reduce that. The good news is that research basically shows now, if we bring emissions of greenhouse gases to net zero as fast as possible, bring the temperatures will stabilize in like 5 years. They'll stop warming just due to our world's ability to take out, to basically equilibrize and help out with that. That's the good news. So the question is, when are we going to start doing all of that, right? And the other good news I would say is that a lot of the solutions for this exist already. Yes, there is some needs for technological advancement, but the technology that we have now produced en masse and implemented across the entire planet can do quite a lot, as it is. So I would say I talk about climate and weather every day and climate change every single day, and I have not lost hope. And I feel still there's still, we can do this, basically.
So Yafet wants to know if I think the heart of the question is, will our ecosystem continue to change in an unpredictable manner, and will weather also become more unpredictable with that?
It's an excellent question in terms of, so our ecosystems are changing on our planet due to climate change, as well as just due to other things humans do to it, right? So encroaching into the urban wild interface is leading to that necessarily climate change, but it's certainly human related. And that'll certainly keep changing. As climate changes, animals are going to be migrating at different times of the year to different places. Invasive species will be able to move farther to the north because it warms. So that's also something we continue to see ecosystems changing across the entire planet. What was the second part of that question again? Sorry, Rick.
I think it's do weather forecasts become less predictable as climate changes?
So I don't think that necessarily that weather. Here's the thing. I think it's going to be more, not for the weather models in and of themselves are soulless things. You put information into them and they spit out an answer. It's like a robot. There's no emotions there, right? But humans who make the forecasts have to look at all of these weather models and make a forecast up. And humans are imperfect. And humans, when having to predict something that they've never thought could potentially happen, can certainly lead to a forecast of them saying, I don't think it's going to be that bad, because it's never been that bad before. Think of the Pacific Northwest heat wave last year. That was so out of the ordinary to be dumbfounding. I'm still at a loss of words for how hot it got. It's inconceivable how hot it got in the Pacific Northwest. I'm shocked, still thinking about how hot it got. Weather models predicted that 7 days in advance. They said that. They said this is going to be a crazy record-breaking event. And as a human being, I'm not going to say it's going to get to 115 in Portland. Portland? Of the Portland, Oregons? Like, that's crazy to think about. I'm not going to predict, oh, it's going to break the all-time record high in Canada 3 consecutive days? That's what happened? Like, the idea of that a human being will think like, oh, you might think more likely that the weather model might be, they're overdoing it, versus you actually being able to see it. But the weather model itself, that soulless, beautiful thing, is able to predict that. So in some sense, I believe it's not like the weather seems to become less predictable. It's going to be more difficult. It's an interesting thread there, not to be more difficult, but into human nature and our ability to say, predicting things that haven't been seen before. And that's one of the crazy things. A lot of times when we think about weather and what's normal, and this idea of predict what's out of the blue, it has a major influence on our ability to figure out like what's crazy, what's realistic that can happen.
I feel like this kind of touches on what we talked about during our prep call, which is, you said, 10 years from now, we're going to look back on this summer as being not that hot. And I think that kind of taps into also Mary's question, which is the current flooding in the Midwest going to be the new normal? Can you talk a little bit about
Sure.
the concept of the new normal?
Sure. So it's shifting baselines pretty much. So a study came out that basically said that human beings, if you ask a human being what normal weather is, a human being will go back about 8 years. Like that's normal to them. So if that's constantly shifting as you go back, 8 years from now, this period is normal. But like if you compare now to the 1990s and 1980s, whew, we're a lot warmer. Things are a lot different. So that's a kind of this idea of shifting. Also, this idea of what can we expect in the future, and in terms of extremes when it comes to weather. And the two most confident things I can say are heat waves and high temperatures are likely to get hotter. Heat waves likely to happen more often, get stronger. Low temperatures at night are going to be grosser, meaning they're going to be higher. It's going to be more uncomfortable at night. And this happens far north where you might not be expecting it, like Canada, like we just saw in England and in Europe this year. And when it comes to extreme rainfall, we're going to see more likely than not, all over a vast part of the globe, extreme precipitation over like 24 hours increase. A warmer atmosphere holds more moisture. So if you have that more moisture, more energy in the system, and you have a thunderstorm, it can rain more. So this idea of shifting baseline to saying, you know, if you ever heard like what is a one, oh, it's a 1 in 1,000 year event. Basically, all that's saying is that there's a 0.01% chance of an event like of that magnitude happening in any given year. Those chances might increase because we're not, those numbers are assuming a static climate, and we're in an anything but static climate. It's changing. So yeah, we could see these things happen more often, these heat waves, these extreme rainfall events, and have to deal with that. And as Rick mentioned, you know, one thing to note that the next decade will be likely warmer than this decade. And the decade after that will be warmer than that decade. So even though it's very, very warm and it's 2022, 2052 is going to be warmer than this. So, you know, this is just kind of, you know, within that time frame, it's, you know, it's kind of where we're at. So this will, in the end, if we don't do anything on climate change, this year will look cool in 2100.
So on that sunny note,
well, we can do stuff about it. We can do it. The rest, it's like the Natasha Bedingfield song. The rest is still unwritten, folks. We can still write our own future. We don't have to do this. We have the power to be able to stop emissions, and then temperatures will stabilize, which is great.
So David would like to know if local weather forecasters actually make the predictions, or if there's somebody else doing that. And I'm going to tie in Jorge's question over here that wants to know whether or not European forecasting models are more or less accurate than American models. And is there any
we're getting into it. So if you look at just a dry statistical sense, the model of the European model, the ECMWF model, performs better than any other weather model in the world. Does that mean it's better every single time? No. We're not talking huge differences between these models. So like, it's not something we're like, I'm going to throw away everything else and just look at that one. That would be a bad idea to do. You need to look at all of them. But currently, if you're going to rank it, if you had to, that would be the best. It doesn't mean that, you know, but each of these institutions that create models do have a whole different structure for it. That group is a consortium of European countries who put money in to produce pretty much that model. NOAA produces a lot more models than pretty much anywhere else on the planet. So we're producing multiple different weather models and wave models and ocean models and pollution models and all these other things, which kind of stress our ability to use all of our super models. So like that's a supercomputers to run all these things. But you know, that's why you tend to hear like, oh, the Euro is better than the US the US model. But on any given day, it doesn't make a difference. You really have to be using everything. And the first question was on
the forecasters. Are they
forecasters? So I'm not a local forecaster. I would say I know a lot of really great local forecasters. And if you want to see somebody who cares more about their local community than a local forecast, I would love to meet that person, because local forecasters are like, they are like your local, they're like your neighbor. They're like the people who do all those local forecasts. And all the ones I know, they make their own forecasts. And there's some really, 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 really great ones out there who do all that thing. So you can trust your local forecaster.
But do they make the predictions, or does somebody hand it to them?
They make their predictions. I think most of them make their predictions. I don't know every single one. I'm sure there are some that are probably just taking something from the Weather Service website, and that's fine. But I feel like most of the big names that you know, they're making their own weather forecasts.
Miriam wants to know, you spoke a little about the jet stream. Can you talk about the Gulf Stream?
Sure.
And, what are the climate change implications with the Gulf Stream?
Sure. So the Gulf Stream is just one branch. It's a surface branch of this broader it's called the thermohaline circulation, how water kind of moves from the surface to the bottom of the ocean and goes across the entire planet. And there's aspects of how that is changing. And this idea, there's a thought process that melting glaciers in Greenland are putting all of that fresh water into the North Atlantic. And the North Atlantic tends to be a salty ocean, because normally what happens is that the water freezes, it takes up a lot of the fresh water, you're left with a saltier and salt water, it'll sink, it's denser, so you have sinking water there. If you freshen the North Atlantic, you stop this process of the surface water becoming and sinking down into the ground, into the ocean. And that can have big impacts, because the Gulf Stream is very, very important. The Gulf Stream is a warm current, right? It is moving a lot of heat towards Europe. If you actually look and see where Britain is compared to the United States, it's in like the Canadian Maritimes on a latitude line. Like New York is like Spain, in terms of like where those are. And the reason can be such its climate, although it's, cloudy and rainy, but it's a lot warmer than, northern Nova Scotia and in those areas. It's because the Gulf Stream is bringing a lot of heat to that area. So if the Gulf Stream slows down a bit, it brings less heat to Europe. And what you can actually see is, and some of this shows up in climate models, as you look at temperature projections for the next century, the Gulf Stream slows down. And while Europe warms, it doesn't warm as fast as other places on the planet. It's still warming though. But I will say this, the Gulf Stream is not going to stop. And the reason why the Gulf Stream will not stop is because the Gulf Stream itself is caused by the fact that the Earth spins. That's why. The Earth would literally have to spin. So unless Superman is out there flying the wrong way around our planet, making it stop, the Gulf Stream will still exist. Because as Earth spins, it creates, by its natural spin, it creates these currents, these strong south to north currents of the Northern Hemisphere on the western side of ocean bases. So we have the Gulf Stream in the Atlantic, and in the Pacific, you have the Kuroshio current that goes off of Japan. Those will always exist, even if they might slow down a little bit. They'll never stop.
So we probably have time for 2, maybe 3 more questions. Mike is asking if you have a preferred website for ordinary people to use when looking up the weather, or does Noah have a good site, obviously? And then also, I'm going to use this as an entry point to see if you can talk a little bit about microclimates.
Sure. So if you're looking for me, I don't have a weather app on my phone. And I don't usually listen to the weather app on my phone. I go to weather.gov if I'm someplace. The weather service forecasters so there's weather forecast offices across the entire country. And I have it pretty much bookmarked. I just go to the website and see what they're predicting. They've been in their communities oftentimes for 15, 20 years. And I don't know oftentimes people who know their local area better than them, because they live in those areas. They're not just forecasting for an area, they're forecasting for their family and friends, because that's where they're forecasting. So that's where normally I go for it. Microclimates, very important. So there can be very specific microclimates, even within cities. We actually do a study at NOAA looking at urban heat islands, this idea that cities can be hotter than rural areas, suburban areas, because of all like the buildings and the roads. And even within a city, urban heat islands can differ. Temperatures can differ up to 17 degrees over the span of 3 miles in a city, comparing a park to an area which is just blacktop. And those microclimates can have really big impacts. Around cities also, I'm at a good thunderstorm right now, folks. It's taking all of my effort not to look outside. It's good thunder too. So cities themselves can create microclimates. Because it's hotter there, it almost, think of it like a little dome over a city, and you can sometimes see thunderstorms form on the backside of cities, because the air is not going to go over it, because it's like a big mound. It goes around it and hits each other in the back end, and you'll see a thunderstorm pop up. So you can have these itty bitty microclimates pop up in different parts of our planet, different cities. You can have little areas when it comes to valleys, and it comes to topography too, very specific climates, depending on where you live.
Sorry, Tom. What makes for good thunder?
Good lightning. So
Loud?
thunder, it's it's loud. This is a good little thunderstorm. I live outside of Washington D.C. It's pretty good right now.
I'm not hearing it on my end, so don't worry about the audio.
Okay.
But so Neil is asking, is AI starting to play a more significant role in making longer term climate forecasts?
So machine learning is doing. There's a lot of research going into machine learning into our ability and pattern recognition as well. Software looking at the benefit now of AI, machine learning, these sorts of things is that we have all of this weather data, which is basically patterns. And now you can basically run it through a series of machine learning algorithms and AI sorts of things, and they can pick out patterns. The key thing behind it, which is the difficulty with it, especially hard times, is being able to attach a physical reason for things when it comes to AI and machine learning. So let's say they see something or they see a pattern that makes sense. What's the physical basis behind it so that we have an idea of what's going on, whether it could be, whether is it happening with our data? And how that, but it's a very burgeoning area of research. There's a ton of corporations now and for-profit institutions, new companies that are forming around this idea of taking that, and especially as it relates to microclimates too, being able to take that data on a large scale and then really amass it down to a very small scale using these AI algorithms to be able to figure that out. So it's a very fascinating and interesting area of research right now.
So Curtis, you're going to get the last say here. Some say the temperature data suggests that higher temperature variance has increased over time as well as higher average temperature. Is that true?
So I'd have to see whether it's on what the time scale is, like a daily basis or an average. Because in general, what we're actually seeing is that the high temperatures themselves aren't rising as fast as the low temperatures are. So the average temperature is increasing. But it's not like it's a fair race. The low temperatures are increasing faster. And the reason for that is kind of similar to, like, let's say you have someone who got an 85 on a test or someone who got a 65 on a test and you let them retake it. Like the person with the 85 only has to go 15 more to get 100, but the low has a lot more potential to do better with that low, to go higher. So the variance itself, there is in the sense of weather whiplash, as I mentioned earlier, there is some evidence of weather whiplash increasing. This idea of going from like really hot to maybe really cold on a daily basis. So that sort of variance, there is some evidence of that, going really wet to really dry. But on a temperature basis, I would say maybe actually a little bit less on a high to low temperature, only because the low is going up faster than the high is.
All right, Tom, that's all we have time for here. Some of you have the link to go over to join Tom on video. Tom, please go ahead and go over there and you can start answering questions if you want. Ann and I will be there in just a moment. In the meantime, thank you so much for coming. Oh, and there he goes. I lost him with that.
He's on his way.
He's running.
And I have my ears in, and I can hear that thunder, and it's not because I can hear it outside, but I can hear his thunder. So
oh, wow. Okay.
I bet some people can. So thank you everyone for being here. We really appreciate it. We will be back in a month. We're doing our events monthly now, and our friends at the American Psychological Association have been working with us to bring you something from the social sciences next time. So watch your inbox for Sachi to get some details out to you, and we hope to see you in a month.
Yeah, so I want to say thanks everybody for the great questions. There were about over 90 of them today. We would have loved to have gotten to them all. We got to as many as we could. Sorry if we didn't get to yours. And I want to re-thank everybody who has joined us at the supporter level and really appreciate your support of these events. I also want to thank Courtney Sloan, Sachi Gervin, Jeff Fishman, Meche Uktabi, the Meche, for technically producing the event. And for some of you, we'll see you over at the VIP lounge. Talk to you soon.